Swayam Prabha. Digital India. Educated India.
Hello and welcome to another lecture of this course Mathematics for Economics Part 1. Today what we shall do the tutorial, and in this tutorial we are going to cover some of the topics of optimization. That is, we have talked about how to find the maximum and minimum of a function, and the economic applications of such problems of maximization and minimization. So today we shall discuss some of the problems related to that. So as you can see on your screen, this is tutorial second part. So this batch of tutorials is focused towards optimization and other topics. So we start with the topic of optimization. So this is the first question that you can see on your screen. A producer has a cost function C of Q equals to AQ square plus BQ plus C. A, B and C are small letters. Under what conditions the function is convex? This is the first part. The second part, the function is concave, and the third part, both convex and concave to the quantity axis. Okay. Just to clarify what is meant by the quantity axis, if you recall, this is how a cost function might look like. So Q, that is quantity of output, is represented along the horizontal axis, and CQ, that is cost associated with the different quantities, are represented along the vertical axis. So this function might look like this, or it could be something like this. So it might have different kinds of shapes. We want to find out, given this particular form, CQ is equal to AQ square plus BQ plus C. This is a polynomial function. Under what condition this polynomial function represents a convex cost function? That is part 1. In part 2, under what conditions this polynomial function represents a concave function, and in the third part, both convex and concave. So the function has to be specified as convex or concave with respect to the horizontal axis, that is the quantity axis. All right, so this is the function that is given to us. CQ is equal to AQ square plus BQ plus C. Now from this I can find out the derivative of the function with respect to Q. The first derivative gives us 2AQ plus B, right? I am just using the power rule. A and B, remember, are constants, and from the first derivative I can differentiate this once more, and I will get the second derivative, d square CQ dq square, and that will simply be twice A. Okay, so this is something we have found out. Now the conclusion will come Under what conditions the function is convex? Now here we use the property that a function is convex if the second derivative is positive, right? The second derivative d square cq dq square is greater than 0. Now, when will this second derivative be greater than 0? It will be greater than 0 if 2a is greater than 0, and 2a is greater than 0 if a is greater than 0. So, this is the required condition. The function is convex if small a is positive. Second part, concave, right? The function is concave. And here, like before, we use the property that the function is concave if the second derivative d square cq dq square is negative. And like before, here d square cq dq square has been found to be 2a. So, 2a is negative if a is negative. That is what I have written here. So, the second part is done. The third part, both convex and concave. Okay, so this is a bit tricky, but it is not actually a big deal, because a function is both convex and concave if the second derivative is equal to 0. In that case, it can be both convex and concave. The idea that is being applied here is that in this case, what I have written here is strict concavity. So, in case of weak convexity, it is greater than or equal to 0, and for weak concavity, it is less than or equal to 0. So, if we have weak convexity and weak concavity, then the relationship of the second derivative with respect to 0 is also weak. So, in that case, the function is both convex and concave in a weak sense if the second derivative is equal to 0, right. So, actually this should be the answer, that the function is convex if a is greater than or equal to 0, the function is concave if a is less than or equal to 0, and the function is both convex and concave if a is equal to 0. Okay. So, we are not talking about strict convexity or concavity, but convexity and concavity in a weak sense, and therefore, we are getting these results. Okay. The average revenue function of a firm is given to be this ARQ. It is given to be 1 plus 3q minus q squared divided by 3. Find the marginal revenue function and verify that it is concave to the q axis, and what is its maximum point. Okay. So, the revenue function is given to us. We have to figure out the average revenue function is given to us. We have to figure out the marginal revenue function. Average revenue function is AR. Let us suppose AR is equal to 1 plus 3q minus q square divided by 3. From average revenue, you can go to total revenue. Let us call that TR. Like average revenue, total revenue will also be a function of quantity Q, and that is found out by multiplying the average revenue with Q quantity, and it turns out to be Q plus 3q square minus Q cube divided by 3. So, this is the total revenue function, and it is a function of quantity. From this, I can easily find out the marginal revenue. the marginal revenue, which we are calling as MR as a function of Q, can be found out from the total revenue by taking the first derivative. So it is calculated to be 1 plus 3, and you have 2Q. 3 multiplied by 2Q gives you 6Q minus 3Q square divided by 3. 3Q square divided by 3 will be simply Q square. So you have minus Q square here. So we have applied the power rule in this case. Marginal revenue therefore is 1 plus 6Q minus Q square. Now find the marginal revenue function and verify that it is concave to the Q axis. We have found out the marginal revenue function. Now how to show that it is concave to the quantity axis? Well, that we have seen in the previous problem. I take the second derivative, right? Here, what is the first derivative? The first derivative is ddq of mr, right? And that is will be, if you differentiate this with respect to quantity, it becomes 6 minus 2q. All right, and you take the second derivative. So differentiating this with respect to quantity, minus 2. So that's what I have written here. You can see that the second derivative is minus 2, which is a negative quantity. Hence, the marginal revenue function is indeed concave, right? This is a property that the second derivative negative means the function is concave. And the last part, what is its maximum point? So if it is a concave function, so it might have a maximum point, right? So how to find that? I take the first derivative of the marginal revenue function, set that equal to 0, and from that I'll get the stationary point. And first derivative I have already found out, it is 6 minus 2q. So 6 minus 2q is equal to 0. That is what I am getting from this condition. And if I solve that for q, I will get q is equal to 3. And this point is actually the maximum point. It is not the minimum point or an inflection point, because I have already seen that the MR function is concave. Okay. Here is a problem from profit maximization, and we are talking about a firm which is in a perfectly competitive market. This firm faces a price P given by 10. So as it is known, in a perfect competition market, the price is constant. So the producer cannot influence the price, it is given. The cost of production function is given by CQ is equal to 4Q plus Q square. Question is, what is the output level of the firm if it wants to maximize its profit? Secondly, what is the magnitude of maximum profit? Okay, so that is the question. What is given to us? The price is given, price is 10. So from this I can figure out the total revenue, TR. TR will be price multiplied by quantity. So this is 10Q. And therefore the profit will be total revenue minus the cost. Cost is known to us, 4Q plus Q square. All right. So the profit function has been found out. I have to now find out the output level where the profit is maximized. All right, to do that, I have to depend on the first and the second order conditions. The first order necessary condition of profit maximization is the first derivative of the profit with respect to quantity is equal to 0. So that boils down to this, right? ddq of 10q minus 4q minus q square is equal to 0, and this is actually 6q. 6q minus q square is equal to 0, and if I take the derivative of 6q minus q square, I get 6 minus 2q, okay, and that gives us the value of q. Q is equal to 3. But we now also need to check the second order condition. So here the second derivative of the profit function that we have to check, it turns out to be minus 2, right? This was the first derivative of the profit function. If you differentiate this with respect to q, you get minus 2. So that is our second order condition, and it is being satisfied, right? So the maximum profit is going to occur at output level 3. And what is the maximum profit level? So that was the second part. For that, I have to plug in this q, that is the maximum point, in the profit function. What is the profit function? It is 6q minus q square. So I just have to put q is equal to 3 here. So if I do that, I'll get the maximum profit to be 9. So that is the answer. Another problem related to perfect competition. A firm in a perfectly competitive market faces the price 5. It has a cost of production given by this. CQ is equal to 3q square minus 595q plus 40,000 if q is greater than 0, and this CQ is equal to 0 if q is equal to 0. So this is the scenario. The cost function is actually it's not a smooth function, because if you put q is equal to 0 in this form, then you get C of 0 is equal to 40,000. But actually it is specified that if q is equal to 0, C of q is not 40,000, it is 0. So you can see that the cost function is having a jump at q is equal to 0. It's not a continuous function. Now the question is this: what is the output level of the firm if it wants to maximize its profit? What is the magnitude of maximum profit? So in that sense, as far as the questions are concerned, the questions are like they were in the previous problem. However, the form of the cost function is very different in this problem. So we adopt the strategy that we had adopted earlier. The price is given, total revenue can be found out by multiplying the price with quantity. So it is 5q. So the profit will be total revenue minus total cost, this. And the first order condition of profit maximization, as we know, I differentiate the profit function with respect to q, set that equal to 0. And here if I do this calculation, it comes out to be 5. From here 5 is coming, then you have 3q square, that will give me 6q, and you have minus 595q, that will give me plus 595, and that entire thing is equal to 0. 5 minus 6q plus 595 is equal to 0. And if I solve that, I get 6q is equal to 600, implying q is equal to 100. We also need to check the second order condition. So I have to differentiate this part once again with respect to Q, and that will give me minus 6. Okay. So, the second derivative is minus 6. Thus, the profit is indeed maximized at Q is equal to 100, because the profit function is concave. What about the maximized profit? So, that is an important question, and as we shall see, this is going to be a very critical question. When the producer has maximized his profit, right, then what is the volume of that maximized profit? Here the maximum profit is occurring at Q is equal to 100. So, I put the Q is equal to 100 in the profit function. So, this is the profit function, 600 multiplied by 100, 100 is the output level, minus 3 multiplied by Q square, that is 100 square, minus 40,000. I just solve this, I just simplify this, and it comes out to be minus 10,000. So, what it basically means is that if the producer has to produce some good, right, if the producer produces Q greater than 0, then the highest amount of profit that he can get is minus 10,000, it is negative. If the firm, instead of producing anything at all, shuts down, then what happens? If the firm shuts down, it does not produce anything. So, total revenue is equal to 0. Remember, at Q is equal to 0, cost is not minus 40,000, it is 0 actually, that is specified in the question. So, therefore, profit will be 0 minus 0, that is 0. Therefore, the optimal output will be 0, and as a result, the optimal profit will also be 0, right. So, that is why I said that we need to figure out what is the maximized profit. If it is turning out to be negative, as it is happening here, then there is no point of the producer to produce anything at all. It will produce 0 amount of output. Okay. Here is a somewhat different question. Suppose the production function of firms is given by this. FL is the production function. A is equal to capital A multiplied by L to the power alpha, where alpha lies between 0 and 1. A is positive. Okay. The price of the good produced is given by small p. The wage rate of labor is given by small w. What is the employment level of a profit maximizing firm? And let us call that employment level is L star. Comment on del L star del w, del L star del A, del L star del P. So, these are the 3 partial derivatives that we have to find out. Secondly, suppose the government announces a policy to give wage subsidy of 1 minus beta multiplied by W per unit of labor employed, where beta lies between 0 and 1. What is the effect on the employment level? That is, what is the effect of this wage subsidy? This is called wage subsidy on the employment level. Earlier the employment level was L star without subsidy. So, how is that going to change with subsidy? So, that is the question. Now, we are going to follow the basic rule. We first find out the profit function and try to see at what level of here employment L. So, L is the decision variable, at what level of employment the producer is going to maximize the profit. So, here is the profit function P multiplied by Q. Q is nothing but the production function minus the cost. What is cost here? There is only one input that we can see. So, cost is minus WL, the wage rate multiplied by the labor employment. The firm will decide the employment by satisfying the necessary and sufficient conditions of profit maximization. This is standard. The necessary condition is this, d pi dl is equal to 0. So, pi is this, right, p multiplied by the production function a l to the power alpha minus wl. I take the derivative of this. So, I get p alpha multiplied by a l to the power alpha minus 1 minus w is equal to 0. This can be actually rewritten as p alpha a l to the power alpha minus 1 is equal to w. Just adding w to both sides, and I'll get this. And this gives me this. I am expressing L in terms of the rest of the parameters, and so L is equal to W divided by P alpha A whole thing to the power 1 minus alpha minus 1. Now, we know alpha is actually less than 1, right. So, alpha minus 1 will be less than 0. So, therefore, I have taken the reciprocal of this, so that the power here is positive. So, this is a positive number. So, what I am getting is L is equal to 1 divided by W divided by P alpha A to the power 1 divided by 1 minus alpha, and let us call this L star. This is the optimal employment level of the producer. As you can see, it is a function of many parameters, principally W, capital A and P. So, these are the parameters of interest. But is the second order condition satisfied? That we need to check, and it is actually satisfied, because if I take the derivative of this part, this was the first derivative, I take the derivative of the first derivative. So, I will get the second derivative. Second derivative is turning out to be this P alpha alpha minus 1 A L to the power alpha minus 2, and this is less than 0, because alpha minus 1 is negative and alpha minus 1 is appearing here. So, this is negative, and that is the second order condition, that the profit function should be concave, and the profit function here is concave if you have the second derivative to be negative. So, we have found out L star, the optimal labor employment. Now, I have to talk about the partial derivative of the L star with respect to these parameters W, A, P, and this is simply manipulation. I have to take the derivative with respect to W of this function, and that after some steps it turns out to be this minus 1 divided by 1 minus alpha P alpha A multiplied by W divided by P alpha A to the power 2 minus alpha divided by 1 minus alpha. Whatever the sign of this entire thing, it is negative, because 1 minus alpha is positive, right, and the rest of the terms are also positive. So, del L star del W is negative. That is my conclusion. Whatever the partial derivative of L star with respect to capital A, and similarly I am not specifying the steps involved here. Here it is turning out to be W divided by 1 minus alpha P alpha A square W divided by P alpha A to the power 2 minus alpha divided by 1 minus alpha, and as you can see by inspection, that this is a positive quantity, right, because alpha is less than 1. So, del L star del A is positive. Similarly, del L star del P is found out to be W divided by 1 minus alpha P square, alpha A W divided by P alpha A to the power 2 minus alpha divided by 1 minus alpha, and this is also positive. So, this is negative, this is positive, this is positive. What it means is that as the wage rate rises, it reduces the employment level, right. This employment level L star is going down. As productivity level rises or price rises, employment level rises. Capital A is can be thought of as a parameter representing the productivity, because look at this, here capital A is occurring, right, and if capital A is high, that means same amount of labor will be capable of producing more output. So, that is why one can think of capital A as a marker of productivity. So, as productivity rises or as price rises, small p is the price, as we can see L star goes on rising, right, because the partial derivatives are positive. Now, we come to the second part. The government announced a subsidy of 1 minus beta multiplied by W per unit of labor employed. For the employer, the cost of labor after the subsidy is announced is given by this W minus 1 minus beta multiplied by W, because this part is given by the government. So, the producer will only have to bear the wage that is paid to the worker minus the part that is provided by the government, and this is simply beta multiplied by W. Now, this is the wage that is actually paid by the producer, and as we have seen earlier, the optimal employment level is decided by this rule, the first order condition, right. This was the condition. The marginal product, on the left hand side you have price multiplied by the marginal product, and on the right hand side the wage that is paid by the producer. Now, what has changed now is that the left hand side has remained the same. The right hand side is no longer W, right. Right now the producer is paying only beta part of that W. So, the producer is paying beta multiplied by W. So, the new condition of profit maximization is this: P alpha A L to the power alpha minus 1 is equal to beta W. From this we can solve for L, the optimal labor employment, and that, like before, is turning out to be 1 divided by beta W divided by P alpha A to the power 1 divided by 1 minus alpha, and let us call this L dashed. Now, I am going to claim that L dashed is actually greater than L star, right. On what basis I am saying this? Remember, beta is less than 1, that means beta W is less than W. Hence, if I take the reciprocal, 1 divided by beta W is greater than 1 divided by W, and that helps us to conclude that this is going to be correct. What you see here is that beta W is occurring in the denominator, right, and here W is occurring in the denominator. And what is the left hand side? Left hand side is L dashed, the right hand side is L star. So, we have just proved that L dashed is greater than L star, which means that if the government provides wage subsidy to the producer, then the producer actually will raise the employment level. So, this is a kind of policy that is often advocated by many people, that if the government wants to improve the employment level in the economy, then what the government can do is that it can tell the producers, look, out of the 100 rupees wage that has to be paid to the laborer, you pay maybe 70% of that, 70 rupees, and I'll pay 30%, that I'll pay 30 rupees, right. In that case, the cost per labor to the producer in that case falls. It falls to 70 instead of 100, and the effect is going to be that the producers will raise the employment level. Okay. Now we come to a different topic, which is, suppose you have a monopoly market, then what happens to profit maximization? A monopolist has the following cost function: CQ is equal to 200Q plus 40Q square. The inverse demand function is given, P is equal to 1200 minus 10Q. First question, what is the profit maximizing output level? Second question, what is the corresponding price? And third, what is the maximum profit? Right? This is the case where you do not have perfect competition, but there is a monopolist, and the monopolist wants to maximize the profit. Then how does he do so? Now, like before, the profit function is total revenue minus total cost. What is total revenue? P multiplied by Q. Cost is CQ. So, PQ, that is total revenue, can be found out by multiplying the quantity with price. Price is obtained from the inverse demand function, that is 1200 minus 10Q. Substitute that here, minus the cost, and this is simplified as 1000Q minus 50Q square. This is the profit function. And as usual, we use the first order necessary condition. We take the first derivative of the profit function, set that equal to 0, that is ddq of 1000Q minus 50Q square is equal to 0. That gives me 1000 minus 100Q is equal to 0, that is Q is equal to 10. What about the second order condition? We have to have the second derivative of the profit function to be negative. Here actually it is negative because this is the first derivative, and if you take the second derivative, you just get minus 100, which is negative. So, the second order condition is indeed satisfied, hence Q is equal to 10. So, that is what we got from the first order condition, Q is equal to 10, is the level of output where profit is maximized. Now, we check for the price at which the producer is going to sell his goods. The profit maximizing price can be found by plugging Q is equal to 10 in the inverse demand function, right. This is the inverse demand function, 1200 minus 10Q is the price, that is the inverse demand function. I put Q is equal to 10 here, I get P is equal to 1100. So, this is the optimal price. The maximized profit can be found by plugging Q is equal to 10 in the profit function. Profit function was pi Q is equal to 1000Q minus 50Q square. I will put Q is equal to 10 here, and if I do so, it turns out to be 5,000. So the profit is 5,000 when the producer is operating optimally. All right. Another problem related to a monopoly market, but this has something to do with the government as well. A monopolist has the following inverse demand function: P is equal to 100 minus 2Q. The cost function is CQ is equal to 60Q plus F if Q is greater than 0, and is equal to 0 if Q is equal to 0, where F denotes the fixed cost of production. What is the profit maximizing output of the monopolist? Is it dependent on F? What is the corresponding price and what is its profit? So this is the first part. You can see that there is a fixed cost involved here. So something similar to this we have seen before, where fixed cost was involved. And now we come to the second part. If a lump sum tax of capital T is imposed, then how does it affect the monopolist's behavior? Monopolist behavior means what is the quantity that it is going to produce, price it is going to charge, etc. If instead of lump sum tax, a fixed percentage tax on profit is imposed, then how does the behavior change? How does the behavior change if excise tax, that is tax on output, is imposed? Okay, so it's quite a long question. We have to do it carefully and slowly to get the answer, but it's not very difficult. Let us first get the expression of profit function. So this is the standard method. The profit function is pi q, is given by total revenue minus total cost. We know the inverse demand function, we put it here, that multiplied by q minus the cost function, which is simply 60q plus f. So this is the profit function, 40q minus 2q square minus f. We know the first order necessary condition is that the derivative of this profit function should be equal to 0, and that will give me 40 minus 4q is equal to 0, or q is equal to 10. Second order condition, I take the derivative of this once again, I will get minus 4, right, which is negative. So indeed the profit is getting maximized here at q is equal to 10. Now what is the amount of profit? The profit is given by pi, which is a function of 10 now. So I have put q is equal to 10 here. That actually simplifies to be 200 minus f, right? This is the maximized profit. Now, as we have seen earlier, this maximized profit, if it is less than 0, then the producer will better stop production, right? Because if he does not produce, then the cost is 0 and the revenue is also 0. So the profit will be 0 if he does not produce. So the maximized profit, if it is less than 0, then it is better to stop production. Thus, we can write the optimal output as follows. It is q is equal to 10 if f is less than 200, because you know what is the maximized profit? It is this 200 minus f. So as long as f is less than 200, then the maximized profit is positive. So in that case, it is worthwhile to produce. On the other hand, if f is exactly equal to 200, then the producer will get 0 profit whether he produces 10 or he produces 0. So both are optimal in this case. And finally, if the fixed cost is more than 200, then the maximized profit is actually negative. In that case, it is best not to produce. So, Q is equal to 0. So, the summary is this: if the fixed cost is high, it is preferable to shut down. If the production is positive, that is F is less than 200, then we can find then the corresponding price and profit as follows. So, price will be just plugging in Q is equal to 10 in the inverse demand function. So, this comes out to be 100 minus 2 multiplied by 10. So, this is 80. So, this is the optimal price, and as we have seen earlier, the maximized profit is 200 minus F. Okay, now we come to the tax part. So, the government has imposed a lump sum tax. What is a lump sum tax? It basically pushes up the cost side. So, the producer has to pay a fixed amount of money to the government. So, that is called a lump sum tax, and that amount of money is given by capital T. So, in this case, the profit function has changed. It has changed to this: the total revenue is PQ minus the cost, and you can see in the cost there is a additional term. It is plus T, right? So, earlier it was just this much, 60Q plus F. Now it is 60Q plus F plus T. And I can simplify this to this expression: 40Q minus 2Q square minus F minus T. Now, what is to be noted is neither the first or the second order condition is affected by the inclusion of the lump sum tax. The profit maximizing output remains the same. Why I am saying this is that if you differentiate the profit function with respect to quantity, that will give you the first order condition, and if you differentiate it twice, then it will get the second order condition. But if you differentiate it once, then these terms will simply drop out because these are constants. So, therefore, the first order and the second order conditions are not going to be affected by the inclusion of these taxes. However, it affects if the producer produces at all or not, right. So, since the first order and the second order conditions are not going to be affected, therefore, the optimal quantity and the optimal price are going to remain the same as long as Q is greater than 0. But whether the producer produces at all or not, that is going to be affected by the inclusion of this lump sum tax. And here is the reason. In the new circumstance, if Q is equal to 10, that is the optimal quantity that has remained the same, the profit is given by this 200 minus F then minus T. So, this has to be greater than 0, right, that we have seen. The maximized profit or the optimal profit cannot be negative, and that boils down to 200 minus F greater than T. Earlier it was 200 minus F greater than 0. Although T does not affect the output, price, profit, if anything is produced, if it is high, greater than 200 minus F, output drops to 0. Actually, this is not correct. Profit is going to be affected, the maximized profit is going to be affected if the producer is producing anything positive, because as you can see, the maximized profit has this minus T component. The optimal output and price remains the same in case of lump sum tax, provided the producer is producing something positive. But if the producer is producing anything positive or not, that is going to be affected by this lump sum tax. Okay, the second question is tax on profit. If a fixed percentage of profit is taxed away, then the post tax profit changes. So, suppose small t be the proportion of profit that is tax. The profit of the producer therefore is equal to, let us suppose it is pi q, it is this 1 minus t multiplied by the profit expression that we had before, right. Here there is no lump sum tax, right, fixed cost is there. However, a portion of the profit, that is t percentage of the profit, has been taxed. So, therefore, the producer is left with 1 minus t multiplied by the profit, and this is simply this 1 minus t multiplied by 40q minus 2q square minus f. You might recall that this expression was the profit expression earlier, right. Earlier means when there was no tax. The first order condition will give the same solution of q as before, as long as tax rate t is a constant. The second order condition will be like before. So, what is being said is that if you set the derivative of this with respect to q is equal to 0, then that will give you just a derivative of this with respect to q is equal to 0, because this is just a constant, right. T is a constant, so this is a constant. So, you are going to get the same first order condition that you got when there was no tax, and similarly the second order condition will be like before, it will be satisfied. Therefore, the optimal output and price remain the same. There is no change in the behavior of the producer, right. The optimal price and output we got earlier were what? Q is equal to 10 and P was, I think, equal to 80, right. So, 10 and 80, optimal quantity and price, those things will hold here also, but there was, remember, a condition whether the producer will be producing at all or not. That depends on what about the profit, it has to be positive. So, this is the maximized profit 1 minus t multiplied by 200 minus f, and that is actually the same condition because 1 minus t is just a constant, right, and this is positive. So, what matters is this part, this has to be greater than 0. So, in case of tax on profit also, the behavior of the producer does not change due to the tax. He will demand the same price, he will be producing the same output as before the tax. One thing will change, that the maximized profit will be less because a part of the profit has been taxed away. Now, we come to the third category of taxes, the excise tax. If there is tax of T per unit on output produced, then the profit turns out to be this. So, this is the revenue part and this is the cost part. As you can see that this is a new term here, minus TQ. T is the rate of tax, and in case of excise tax, the quantity is being taxed, right. How much quantity the producer is producing, based on that the producer has to pay taxes to the government. So, the total amount of tax it has to pay, which is TQ, it is a product of the tax rate multiplied by the quantity it has decided to produce. Okay, so, this is the cost function, new cost function. Now, again I apply the first order condition, that is the derivative of the profit function with respect to quantity, set that equal to 0, and that gives me this 40 minus 4q minus t is equal to 0, and you get the solution of q as 10 minus t divided by 4. Just for comparison, earlier when there was no tax, no excise tax, the quantity, the optimal quantity was simply 10. Now that optimal quantity is 10 minus T divided by 4. So, the optimal output changes after the imposition of tax, it falls by a bit. The second order condition will be satisfied like before, because if you take the derivative of this with respect to q, then this part simply drops out, so you get minus 4. So, the second order condition is satisfied. Correspondingly, the optimal price also changes, right. So, I put the optimal quantity in the inverse demand function. So, 100 minus 2 multiplied by the quantity. So, you get 80 plus T divided by 2. So, the price actually has gone up due to the tax. Earlier it was 80, now it is 80 plus T divided by 2. The optimal profit will decline due to the excise tax, and as we know, if the profit goes below 0, then the optimal output is 0. Optimal profit will decline because of the tax, because the quantity is being produced less, the price is charged more. So, obviously, the profit will decline. What is the conclusion? Unlike lump sum and proportional profit tax, the excise tax affects the behavior of the producer, right. In lump sum tax or proportional profit tax, there was no effect on the optimal quantity the producer was producing or the optimal price, except for the fact that whether the producer is going to be producing at all or not, that was getting affected by the tax. Other than that, there was no change on the optimal quantity and price. But here, in case of excise tax, the optimal quantity and price is getting affected. Here is another problem from optimization. Let CQ be the total cost of a firm producing Q units of output. CQ is differentiable. The average cost function is given by AQ is equal to CQ divided by Q. Prove that AQ has a stationary point at Q star greater than 0 if and only if the average and marginal cost are equal at Q star. Okay. So, as given in the question, AQ is the average cost is equal to CQ divided by Q. CQ is the cost function. Now, if the derivative of the AQ, the average cost, is equal to 0 at Q star, then I can call Q star as a stationary point of the AQ function. So, I take the derivative of the AQ function, the average cost function, right, and I apply the quotient rule, right. So, I get Q multiplied by C prime Q minus CQ divided by Q square. Now, if we have a stationary point, then this has to be equal to 0, right. The derivative has to be equal to 0 for a stationary point, and that means that the numerator is equal to 0, which is equivalent to saying that Q multiplied by C prime Q minus CQ is equal to 0, and I can take CQ to the right hand side and divide both sides by Q. That will give me C prime Q is equal to CQ divided by Q. And what is CQ divided by Q? It is the average cost. So, marginal cost is equal to average cost. This is what we are getting from this condition that the first derivative is equal to 0 of the average cost function. If at Q star marginal cost is equal to average cost, then at Q star AQ has a stationary point, right, since TDQ of AQ will be equal to 0. Okay. So, that is what we have just seen. So, if the marginal cost and average cost are equal at a particular quantity level Q star, then that actually means that the first derivative of the average cost is equal to 0, which means that Q star is a stationary point. On the other hand, if at Q star AQ has a stationary point, then by the above demonstration, the first derivative of the average cost is equal to 0, which means this is 0, and that actually means marginal cost is equal to average cost. Hence the proof. So, it is a basically if and only if kind of statement, right. If you have a stationary point, then marginal cost is equal to average cost. On the other hand, if marginal cost is equal to average cost, then you have a stationary point of the average cost function. All right, here is another problem related to monopoly. A monopoly sells in the domestic market where it should be monopolist. So, there is a monopolist firm which sells in the domestic market where the demand function is given by this Q1 is equal to 30 minus 1 divided by 2 P1. The cost of production is given by CQ1 is equal to 20 Q1. Solve for the inverse demand function and hence obtain an expression for the profit function. Okay, so, this is the first part. Now, notice what we are given is not the inverse demand function, we are given the demand function where quantity is a function of the price. So, first thing to do is we have to find the inverse demand function, and from there one can find the profit function. Now, the demand function is given by this Q1 is equal to 30 minus P1 divided by 2. Now, that is equivalent to 2 Q1 is equal to 60 minus P1. I have multiplied both sides by 2, and from here I will get P1 is equal to 60 minus 2 Q1, right. Now, actually I have P1 as a function of quantity. This is the inverse demand function. Now, you might be wondering at this stage why we are talking about this subscript 1 all the time. That will become clearer later on when we introduce another market, right. Now, the inverse demand function has been found out. So, therefore, the profit function can be found out by using that profit is equal to revenue minus cost, and therefore, I get 60 minus Q 2 Q1. So, I am using P1 multiplied by Q1 and minus the cost is 20 multiplied by Q1. So, this is simplifying to be 40 Q1 minus 2 Q1 square. So, this is the profit function pi 1. Second part, is the profit function concave? Well, I can find that by taking the second derivative of the profit function, and second derivative of the profit function is minus 4, which is negative. So, the profit function is indeed concave. Third part, find the profit maximizing output and price. So, again this is standard. I maximize the profit. For that I use the necessary condition. So, I take the first derivative of the profit function, set that equal to 0. That gives me this 40 minus 4 Q1 is equal to 0, or Q1 is equal to 10. This is the profit maximizing output. So, the profit maximizing price is given by the inverse demand function, which was P1 is equal to 60 minus 2 Q1. right? P1 is equal to 60 minus 2Q1. So here I put Q1 is equal to 10, right? So I'll get 60 minus 20. So the optimal price is 40. So this is the answer. The optimal quantity is 10, optimal price is 40. All right, here is the foreign market. So I'll get another subscript here. Suppose the USA, a foreign country, lifts import duties for this product. For this product means the product that is produced by the monopolist firm. The firm can now sell to the US market where the demand function is Q2 is equal to 33 minus P2. Let us ignore the transportation costs of sending the goods to the USA, so that the cost of producing is the only cost to sell in both the markets, and it is given by this. So, this is the cost function. C of Q1 plus Q2 is equal to 20 multiplied by Q1 plus Q2. So, basically it means that it does not matter where your good is being sold, the cost of production is same. So, we are ignoring the cost of sending the goods to the foreign country, and the cost is just 20 maybe rupees per unit, right, and there is no fixed cost. So, the total cost of producing Q1 plus Q2, total amount of output, is equal to 20 multiplied by Q1 plus Q2. So, here is the fourth question. What is the inverse demand function of the USA? That is, in the USA market, the American market, the inverse demand function is what? Well, the demand function is given Q2 is equal to 33 minus P2. From here, I get P2 is equal to 33 minus Q2, right? This is the inverse demand function. However, this has to be valid if Q2 is less than or equal to 33. Otherwise, if Q2 is higher than 33, I cannot say that P2 is negative. In that case, P2 should be equal to 0. Here is the fifth question. Write the expression of total profit function. Argue that it can be treated as a summation of two independent profit functions. Total profit function will be the profit from the first market and the profit from the second market, right? But remember, the cost is coming from one source. So, total cost is this, whereas total revenue is this. So, total revenue minus total cost, and total cost, as we have seen, it is just 20 multiplied by Q1 plus Q2. And as you can see, I can take all the Q1 terms in the first bracket and all the Q2 terms in the second bracket. Here, the first term in the square brackets is the profit from the domestic market, and the second term is the profit from the US market, right? That is quite evident. This is the quantity sold in the domestic market, this is the price obtained in the domestic market, this is the cost of production for the goods sold in the domestic market, right? And here is, these are the expressions for the foreign market. So, what we are getting here is that these two terms are independent of each other. While the first is a function of only Q1, the second one is a function of only Q2. So, the interesting part of this problem is that the total profit which the firm is obtaining by selling the goods in two different markets is a completely decomposable function. Decomposable in the sense that you can decompose the function in terms of profit from the first market and profit from the second market. There are no composite terms. There is no term involving, let us suppose, Q1 and Q2 together, right? So, therefore, the maximizing the total profit can be done by maximizing two independent profit functions separately. right? There is something called maximizing a function which has multiple variables. Here it is actually a function which has multiple independent variables q1 and q2. But the fun part of this profit function is that it can be seen as composed of two independent functions. Each function has only one independent variable, and therefore I can optimize these two functions separately. I can do that because I know how to maximize a function with a single variable, and that will give me the solution. Okay. Solve for profit maximizing outputs and prices. So, this is the sixth part, right. This is, I think, the last part. Solve for profit maximizing outputs and prices. Now, for the first part, which is the profit maximization in the domestic market, that we have already done, this part, right. The quantity was 10 and the price was 40. Q1 was 10, P1 was 40. So, that was done. Now, we can do the profit maximization for pi 2. Pi 2 is total revenue from the US market, this minus the cost, and this is standard. I take the derivative of this with respect to Q2, set that equal to 0, and it will give me ddq2 of 13 q2 minus q2 square, and that is 13 minus 2 q2 is equal to 0, and it gives me the solution q2 is equal to 6.5. So, quantity that is going to be sold in the US market is 6.5, right, that is the answer, and that is going to maximize the profit from the US market. 6.5 maximizes the profit function, since the second derivative of the profit function is minus 2. So, the second order condition is satisfied, because if you take the second derivative, it is minus 2. This implies through the inverse demand function, the profit maximizing price in the US market, that is P2, is equal to 33 minus Q2, right. So, 6.5 is the quantity Q2. So, I am getting 26.5. Okay. So, that is the price that is going to be charged in the US market, P2, 26.5. Here is an observation. Although the good that is being sold in both the markets is the same, the price in the US market is less than the price in the domestic market. P2 is 26.5. What was P1? P1 was 40, right. So, there is a gap between the price that is being charged for the good in the domestic market, which is a high price, and the price that is charged in the US market, right, P2. Although the good is just the same, but the producer, while maximizing the profit, is charging different prices in different markets. This phenomenon is called price discrimination. It is the price discrimination of the third degree in microeconomics. Okay, I think I'll stop here today, and I'll pick up the thread in the next lecture to cover more topics from the tutorials. Thank you for joining me.